Hello, everyone. My name is Jesse Markowitz, and I'm a data scientist with a background in science education. With my project, I'm working to improve safety for cyclists in New York City by taking some first steps towards automating enforcement of vehicles parked in bike lanes. This is a very personal issue to me because my bike is my primary mode of transportation around the city, but I constantly have to leave the bike lane and merge into moving traffic because of vehicles that are stopped or even parked and left in the bike lane. It's a big safety issue, and it's going pretty much unenforced at this point. But last month, the Department of Transportation announced that they were interested in implementing an automated system for enforcement that would help stop vehicles from stopping in the bike lane. And there aren't too many details yet about what this system would look like or how it would be implemented, but there's plenty of existing systems that use cameras to enforce things like red light or speeding cameras, or the automated bus lane enforcement system that's been in place since 2010. So I took some clues from those systems, and I'm imagining for my case that there would be a stationary camera on the street looking down the length of the street to get as much of a view of a bike lane as possible. And this system would need to identify not just if there's a car or vehicle in the camera frame, but specifically if there's a vehicle blocking the bike lane. So to accomplish that, to teach a model to do that, I had to first assemble and organize a brand new data set of images, which I got from a couple of sources, but primarily from manual collection, which just means me biking around the city and taking hundreds and hundreds of photos of bike lanes, which luckily there are many hundreds of miles of bike lanes in the city. So this wasn't too difficult to get, but it was time consuming. And I selected images carefully to fit with that use case that I'm imagining for the system and to give my model the best shot for success. So on the left, you can see a couple of examples of images I used of vehicles obstructing bike lanes. And I was careful to make sure that the whole vehicle was visible, the whole front or back end. It's clearly showing the vehicle, including part or all of the bike lane, and varying distances from the camera. And then for all photos, especially in empty bike lanes, I wanted to make sure there weren't too many other obstructions like cyclists or pedestrians, and that both sides of the bike lane were visible, with and without other vehicles in the frame. I tried to keep things consistent with the framing of the image. So I ended up with over 1,800 images, which might sound like a lot, but for an image classification task, it's a very small data set, especially because I had to set aside a couple hundred images for testing. And a small data set like this one is problematic because it means maybe the model won't learn well enough to be able to distinguish the two types of images, or that it'll learn really well on that small data set I have and then not really be able to generalize. So I did a couple of things to try to take care of that issue. First, I used something called image augmentation, which works by altering images as they're shown to the model. Some of them are flipped and mirrored, some of them are rotated or shifted or brightened or darkened, or a combination of any of those at random. And this strengthens the model because it gives it more variety to learn from in a way that mimics and anticipates the possible characteristics of new images that it might see after training. And I also used transfer learning. That means that I took this big, complicated multi-layered model. It's called VGG16. And this model was trained on a data set of 14 million images of 1,000 different categories. So it's really good at recognizing many, many different patterns and everyday objects. So by changing just the last few layers of this model to my own layers, I can take all of that knowledge that it already has, all that pattern recognition, and apply it to my task. And when I did that, the model worked out pretty well. It got over 90% accuracy at determining which were photos of open bike lanes versus bike lanes that were blocked by a vehicle. And it also did especially well on precision, which just means reducing these false positives here. This number 4 means that there were 4 images out of this test set of 100 where it was actually an open bike lane image and the model went, haha, it's being blocked by a vehicle. I want to reduce those false positives because I wouldn't want to send someone a ticket who wasn't actually violating the law. I also wanted to make sure that we could tell what the model is doing, because these neural network models are notorious for being black box models. We don't actually know how they're making their decisions. But there's more and more tools coming out that open that box, and Lime is one of those. So here we can see Lime telling us that this model that I tested it on, it's looking around the image, some cars that are highlighted red, it's thinking, this might be a blocked bike lane image. But then it looks further into the image and it sees where the bike lanes come together towards the horizon line, and that they've converged without any obstruction, and it correctly classified it as an open bike lane image. At least I think that's what it's doing. That's what Lime is suggesting. And here's a correctly classified image of a car blocking the bike lane. You can see I was very excited to see it was doing exactly what I hoped it would do. It's recognizing the bike lane, it's recognizing the space between those lane lines and the vehicle that's blocking them. So I think a model like this, even when it is trained on such a small data set, can still be pretty accurate and in use with this automated enforcement. And that will make the streets safer through increased efficiency and consistency of ticketing, while also decreasing the need for active police engagement. So they don't seem very interested in enforcing this rule. To make my model stronger, I would definitely need a lot more data to strengthen it and give it more variety to learn from. And especially I have to incorporate object detection. So that means not only determining, is this a picture of a blocked bike lane, but identifying and locating exactly which vehicle is blocking the lane so that only that vehicle and that driver are mailed a ticket. Thank you very much.